graph embedding. So when we have a H, which is a sparse graph or small graph, then we want to find some sufficient condition on G so that we can guarantee that we can embed H into G. So we learned about two-run problem, which deals with fixed small h and large G. We found certain sufficient condition on the number of edges on G, which guarantees this embedding. And yesterday afternoon, we showed that in the case when H is comparatively larger, so H also has some number of vertices which is a function of n, so especially some small number epsilon times n vertices, vertex graph H, and if H is a bipartite and has maximum degree bounded, then it embeds into any n vertex graph G with at least epsilon n square edges. So today we will learn about another technique which also gives this kind of embedding. So we have large graph G and comparatively not so small, smaller than G but not so small graph H, and we want to find the embedding of H into G. So for given graph H, let's say very simple graph, right? So okay, R partite graph H. In this case, R is 3 and H is triangle. Then if we want to embed it into G, then what would be the most easiest case? So one of the easiest cases when, if G is complete three-partite graph, then we are free to embed it. So just these vertices in here, so one color class into here, and one color class here, one color class here, then anyway we want, anyway if we embed it in injective way, then we get an embedding. But this is too special case, too strong condition, so it's not that much useful. Then what other, condition we can give? One other thing we can consider is that when you have n vertex, say here and here and here, and we can consider random graph. So for each pair of vertices, we flip a coin, and if it's head, we add the edges, and if it's tail, we don't add an edge. Then in the resulting graph, we can easily show that with high probability, H embeds into this graph G. So for example, in triangle case, if we take arbitrary triple, then the probability that that triple forms a triangle is 1/8. So with half probability, half probability, there is an edge. And if all three events occur, then H embeds into G. And we can take three vertices and three vertices in all disjoint way, then we get n triples. And the probability that all of them are not triangle is 7/8 to the n. So with this probability, so almost 1, with probability almost 1, there is at least one triangle, so we can embed H into G. But still, most of the graphs are not random. So random graph is very special incident, and to be precise, it's not even a graph, it's some graph model. So it's probability model. So then this is not just for this triangle. Any small h we can do this. So this is very good for us because any small h we can, almost freely embed it into G. So we know that this randomness implies this embedding. But this is too strong condition, so it is not so much useful because most of the graphs that we want to deal with are not random. Actually, what I just said might be not true, but anyway, so let's not go into too much detail. But then what we want to do is we want to find a weaker condition than this. So what essential region we get this embedding for any small h. So there might be another region say P, another property P, that the randomness implies that, and this actually implies this embedding of any small h. And then this might be quite weak condition so that we can find it in lots of graph. Then that would be the ideal case. So what would be this? So this kind of condition, that randomness implies something and that something implies another result which also comes from randomness, we usually call it pseudo randomness or quasi randomness. So I mean there are several such kind of property, and one of them we will learn today is regularity. So to define regularity, we need to define what density is. So for given graph G and two disjoint vertex set A and B, we say density of G between A and B be the number of edges of G between A and B. So this denotes the number of edges of G. This is not rho, this is E. Yes. Between this vertex set A and B. So if we have A and B, and let's say here we have 2 vertices, 3 vertices, and say 4 edges, then this is, 4. And then we divide it by size of A times size of B. So because size of A times size of B is the maximum number of edges we can have between A and B. So in this case, this is 4, and this is 6, so density is 2 over 3. So we define this density. And by using this, we want to define epsilon regularity. Yep. So what would be the, so we want to find some condition which random graph satisfy that condition, right? So in terms of in terms of density, so if we consider, say, random bipartite graph between these two, and then consider this density. So random graph, every time we flip a coin with the probability half, we get edge, probability half, we don't get edge. Then if we take certain parts and certain parts and count that, compute the density, then that should be close to half if both sets are, large enough. Because when you flip a coin lots of time, you get the number of heads you get should be close to half. So as long as this is large, this is, not too small, large, then density should be half, and here also density should be half. Here all density should be half. So in some sense, these are uniform, almost uniform regarding its density. So that's the property that we want to capture. So we say that a pair, we either say G is epsilon regular or that this pair is epsilon regular. We sometimes use the both notation, language. But let's define it this way. So we say the pair AB is pair of disjoint set, disjoint set of vertices is, we say epsilon D regular. In a graph G, if the following holds, and the following is what I described. It's uniform in the sense of density. So what it means is for any set A prime, which is subset of A, and B prime, subset of B, which is not too small. So A prime has size at least epsilon times A, and B prime has at least size epsilon times B. So epsilon is some small number which measures, how uniform it is. So if epsilon is smaller, then it's more uniform. What we have is its density between A prime and B prime is very close to D. So it's either at least D minus epsilon and at most D plus epsilon. So what it means is exactly what I described. So if we have A and B, and we take arbitrarily not too small set A prime and arbitrarily not too small set B prime, then the density between these two should be close to D. And epsilon measures the error it can have. So it could be slightly off D, but not too much, assuming epsilon is much smaller than D. And we say this epsilon regular if it is epsilon D regular for some D. So sometimes we omit D if it's not really necessary, and we say epsilon D plus regular if it is epsilon D prime regular for some D prime at least D. So it is easy to see that all the previous example, not easy, but yeah, all the previous examples that I showed you actually satisfy this. So if we consider complete graph, complete bipartite graph, then no matter what A prime and B prime we get, its density is 1. So it's 1, 0, then regular. And
0, 1 regular.
0, 1 regular. Thank you. Yeah. And if we consider random graph, we take A prime and we take B prime, satisfying this condition, and we can use Chernoff inequality to show that the probability that it has density very close to D is actually smaller than something like 2 to the negative.
Twice e to the negative.
Yes, so, yeah, right. So, yeah, I was just gonna write something equivalent but different, but twice times e to the, negative. You can show that some smaller number times n square, something like this. So this small number may be some different epsilon, and then you can show that the number of choices that we can take A prime is 2 to the n, and the number of choices we can take B prime is another 2 to the n. So by union bound, we can show that there exists a bad set is at most this, but e to the n square is much smaller than 2 to the n, 2 to the n. And n is large, then this is major term, so equals to 0. So we can actually show that it's one of the exercises, so we can actually show that this random graph satisfies this epsilon regularity condition with high probability for any small epsilon. So we define this epsilon regularity. Then if this were to be useful for us, we need to prove two things. So one, we need to show that this concept is useful for graph embedding. So once we have some structure with this epsilon regularity, then we should be able to use it to graph embedding problem. And two, we should show that this is, weak enough condition so that we can apply to other graphs. So for general problem situation, if we have certain graph G, we should be able to, find this structure inside of G in some easy way. So these two things are, necessary in order this to be useful for us. So today we will show those two. We will not show. We will explain those two are actually true. So for that, let's prove one lemma. So in order to show that this is actually useful for graph embedding property, graph embedding problem, what we want to first show is this lemma. So later what we want to do is we want to prove some lemma showing that if we have certain structure with this epsilon regularity, then we can embed other graph into that structure. So how we will do it is just like how we did at the last theorem in the yesterday. In the yesterday, when we have some H and G, we use dependent random choice to find some U. And we have these vertices, and each time we embedded one vertex into nice set. And while doing that, we are caring about these vertices. So these vertices has initially some candidate set. This can be embedded into any vertex here, but as soon as these are embedded here, its possibility for next embedding is shrinked. But we want to show that it doesn't shrink too much. That's what we showed last time. And then we can keep do that so that at the end, each vertices still have large candidate. So in that, so in such an embedding, the one important thing was that if this has this candidate set, then when we embed this into another vertex set, another vertex here, so that this vertex still has large number of neighbors inside of this candidate set. So let me say it again. So let's say, this is already embedded. And then when we embed this vertex, before we embed this vertex, say this vertex has target set here, the candidate set here. So far, some of its neighbors has been embedded. So this can go into any one of these vertices, but not these vertices, because if it goes to here, then its neighbor and here are no edges. So at this moment, there is this candidate set that this vertex can. But now when we embed this into here, we have to update this so that its image is this B, then it's shrinked into this smaller set, which is also neighbor of B, right? But we want to make sure that it doesn't shrink too much. So what we need is, if we take arbitrary set, which is current candidate set, we want to show that there are many vertices which has many neighbors here. In that case, out of that many vertices, we can embed, this vertex into one of that many good vertices. So that's what this lemma 4.2 is for that. So what we want to do is when we have A and B, which is epsilon regular, then whatever set, did we take it from A or B? B. So whatever set, say B prime we take, we want to show that here there are many vertices which have large neighbors inside of B prime, not only in B. Then it will be useful later in this manner. So if A, B is epsilon regular, epsilon D regular, in a graph G, and let's say we have B prime, which is subset of B, whose size is not too small. Then what you get is what I just explained. So the number of vertices in A, whose degree in G to B prime is not correct, so not too far from D times B prime, is only small amount, 2 epsilon size of A. So again, we have A and B, and whatever B prime we take, it is not too small. Then there are many vertices here. So most of the vertices here has correct degree inside of here. So what I mean correct is at least t minus epsilon and at most t plus epsilon. So lots of time what we actually need is this one side. So we are happy if it's not too small, but what we can actually prove is that it's also, we can actually make sure that it's also not too big. This? No, d minus epsilon. Okay, sorry. So not too small. So what I mean is that the number of vertices who has too few neighbors are small. So most of the vertices has at least this many neighbors. That's the actual property that we will use. But what we can prove is that this is also small and this is also small, so that most of them are very close to D. So let's prove this lemma 4.2. Yep. Maybe we can keep some lemmas here and proof here. The proof of lemma 4.2. So this comes from the definition of epsilon regularity. So we read a to the minus is all vertices which has too small degree to this b prime. And a plus is all the vertices which has too big degree in B plus. Sorry. Thank you. Yeah. So let's just show that we want to show that this is small and this is small. Then we are done. Their sum is also small. So let's say the first one is not small. If say a to the negative has size at least epsilon times a, then what happens? So we have this a negative and b prime inside of a, inside of b. And all vertices here have at least d plus d and most d minus epsilon times b square edges. Then automatically we can compute that the density between these two is less than d minus epsilon. But which is contradiction that we take not too small set a minus, not too small set b prime, and density between them is too low. That's contradiction to the definition of epsilon regularity. So we can write that in more rigorous way. Then density between G, the density of G between A minus and B prime is just we add all the number of edges here, and we add it in terms of vertices in A minus. So all the degree of these vertices into B prime, and we divide by size of A minus and B prime. Then all of these vertices has at most t minus epsilon B prime degree. And how many of them? A to the negative many of them. And we divide by A negative times B prime. Then it's strictly smaller than, this is strictly smaller. This is strictly smaller than d minus epsilon. So if this one is bigger than epsilon times a, then that's the contradiction to the epsilon regularity. So contradiction, we get this should be smaller than epsilon a. Likewise, so everything same with the just plus and the flip the inequality. We can say likewise. We can also show that a to the plus is also smaller than epsilon times a, which proves the lemma. So now we prove this lemma. So we can prove the embedding lemma, which says that this epsilon regularity structure is useful for our graph embedding problem. So this is called embedding lemma. Say delta and n are integer. So there are n is the number of vertices that we will use, and delta is the maximum degree of h. So h has maximum degree bounded, and G has this epsilon regularity structure. Then we want to show that we can embed h into G. And we need to ensure that this epsilon is small. So epsilon is error bound. So if epsilon is too big, then the condition is too weak. So we want some bound on epsilon. But again, this expression is not really important. This is just for technicality. We can just think that the epsilon is quite smaller than d or delta. Then we suppose that the G, the vertices of G are partitioned into V1, V2, V sub R, and each Vi has size n for all I. Let's not put period here. And it admits the structure of epsilon regularity. And V sub I and V sub J is epsilon regular with the density at least D for all distinct I and J between 1 and R. So G has the epsilon regularity structure that we described before. And then H should be sparse and have also compatible structure. So H is an R-part-type graph. With partition x1 to xr. So this is R-part-type graph, and it has partition into R independent sets. And with, say, maximum degree of H is bounded, we need this condition that H is sparse. Otherwise, it is very hard to embed a dense graph into another graph. And let's say each xi is smaller than epsilon n. So remember that now we are considering the case H also has, size of H also can grow with n. But still, we ensure that the H is sufficiently smaller than G. So each xi is sufficiently, so Vi is the parts in G. So xi is still smaller than some constant times n. For each I between 1 and R. Then there exists an embedding pi of H into G such that pi of xi is subset of Vi. So we can embed this H into G so that each xi is mapped to Vi. So we can specify to a certain degree that which vertices must go into which sets. So in other words, if we have H, and then let's say this is 3-part-type graph, and maximum degree is bounded, and x1, x2, x3, and we have G, and V1, V2, V3, and epsilon regularity, epsilon regular with the positive density LSD. So if this was complete graph, complete graph, complete graph, then it is easy to see that we can embed this so that the x1 go to v1, x2 go to v2, x3 go to v3, and every edge embed to edge. So for complete graph it is easy. But even if it's not complete, if it's epsilon regular, epsilon d plus regular for some d and epsilon, and h has bounded maximum degree, then we can do the same as if this was complete graph. So we can embed these vertices here, this vertices here, this vertices here accordingly, so that we get embedding. So we can prove this.
So do you need to make every pair to be epsilon regular, or?
So to be precise, okay, if let's say this was empty, then we can delete this condition. This doesn't have to be epsilon regular. But if there is an edge, it should be.
Right.
Yep.
Maybe depending on the graph H.
Yeah, depending on graph H. If graph H has looks like this, so there is no edge, then we only need epsilon regularity here. So this doesn't really matter. I think that's exercise later. Yeah, that's exercise 4.7. Actually, so this is simple form. We can ensure a bit more. And one of the exercises about strengthening. And indeed, later we will use that strengthening. So, yeah, I recommend you to prove it 4.7. Actually, proof is very similar with the small detail changes. So it's really doable. So, proof of lemma. So what as I mentioned before, what we essentially will do is like yesterday, we used the dependent random choice. We have x1 and x, say, I don't know, a, and y1 and yb. And we embed this into this set u. And here we define nice sets, which has large neighborhood here. And we, one by one, we embed it. Why are embed these vertices? We were being careful about how its candidates shrink. So initially, every vertex can go to every vertex. But when we embed one of its neighbor, now y can only, this goes to say v1. Y can only be embedded into neighborhood of v1. So vertices that y1 can go shrinked. And then later, if we embed the next vertex, this vertex into here, it shrinks again. And we make sure that it doesn't shrink too much. But one good point in here is that we have these two disjoint vertex set. We are embedding this, and then we don't care about, candidate of these vertices because this is already independent set. And then we only care about candidate of these vertices. And then once we are done, and we just don't care about candidate anymore, and because this is again independent set, so we just embed it without thinking further about the candidate set. So it was convenient because this role was divided. But now what we want to do is we want to merge this role. So now we don't have this distinction. So every vertex has candidate. And then on the fly, we embed one by one, and we care about candidate set for every vertex. So let's say x1, x2 to say xh. So h is the number of vertices in H. Be the vertices of H. Be arbitrary order. And each vertex belongs to one of these vertex set, capital Xi. So suppose that and let psi, is it psi? Yeah. Greek letters sometimes confuse me. Okay. It is, yeah, psi I be the index such that xi is in x psi I. This is small x, this is capital X. Let me make it more big. Then we will construct the embedding one by one. So we will embed one vertex by one vertex. And while doing that, we want to care, we want to keep thinking about every vertex, every unembedded vertices, candidate set. We will construct, construct embedding pi by phi xi is bi for each I in turn. So we start from x1 and we x2, x3, x4, so one by one. So let C sub I of j be the possible candidate of, say, B sub j. So image, which is image of x sub j, after we define, so after we embed pi of x1 to pi of xi minus 1. So we are about to embed xi. So let's say we are about to embed, say, x1, x2, and x3. So we have embedded 3 vertices, and we are about to embed x4. At that time, let's say here we have x7, which is not yet embedded. So at this moment, x7 has its candidate set. So vertices that we can embed x7. If x7 is a neighbor of x3, then at this moment, so we have embedded that. So x7 must be embedded into neighbor of x3. So in that case, at that case, its candidate set is neighbor of x3. So to be more precise, so we consider this vertex set that this can go into. This should go into this vertex set, right? Oh no, sorry, V. This should be mapped into here, right? Because we want to embed all xi into bi, and this x7 is into x psi 7. So it should go into here. And also it should go into neighbor of x3. Sorry. So neighbor of B3. B3 is image of x3 in G. And then also we have to delete B1, B2, B3. So some of them might be already used. So we want it to injective. So that's the candidate set for this at the moment, right before we embed x4. So that's this. So we initially have we have C sub 1 j is exactly B psi j. Because C sub 1 means that we are about to embed x1, so we haven't embedded anything. If we haven't embedded anything, then this can go into any vertices in here. So we have this initially. And then now we embed one by one, and we keep track of how much is shrinked. And then we want to show that it never shrinks too much. So assume we have embedded x1 to, say, xi minus 1. So we are about to embed xi. So that means b1 to bi minus 1 are all determined. And then we assume that all of ci j is at least delta plus 1 times epsilon n. So this is our induction hypothesis. So if I is 1, then we haven't embedded anything, and we have initial candidate set which is definitely bigger than this, which has size n, which is because here this has size n, so n is bigger than this number. So initially, if I is 1, this is satisfied, and we embed first one, and we I mean, we embed 1, 1, 1, and then assume that we have embedded I minus 1, and this is still satisfied. So we want to show that after one more embedding, this is still satisfied, after one more, this is still satisfied, and we can keep going until we embed everything. So this is our induction hypothesis. Then we want to show that there is the choice of B sub I, which is image of X sub I. So there is choice so that it doesn't shrink any other candidates too much. So we want to select image of Xi, which is Bi, and it should be inside its candidate set. So candidate set of Bi Xi okay, and yep. And it doesn't shrink C sub I J too much for J bigger than I. So again, like the last time, when we embed Xi,
so it doesn't shrink Ci plus 1j?
Wait, so I'm already confused with the I and J. Wait, which one?
No. So if you shrink Cij, then you get Ci plus 1j.
Yes, so this 2 I plus 1, okay, I plus 1J, okay. Yes. So, like last time we did this dependent random choice, and then when we embed Xi into certain vertex here, we have this y1 and yb, and out of these vertices, only small fraction was affected. Those, so candidates of y1 and yb shrink if they are neighbor. If they are not neighbor, it doesn't shrink, right? So in this case, so those vertices are the possible dangerous vertex, which might shrink too much. So let's say those vertices are A. Let A with all xj, which is neighbor of xi in H, and j is bigger than I. Because if j is smaller than I, it's already embedded, so we don't have to worry about that. And let's say that's x sub s1, x sub s2, and x sub sp. And p is at most delta. Okay, so let's say we have this H, and we have xi here. And then there is x s1, x s2. And then we have B. And so this is G. We have this and this. So now this has this candidate. So this should go into one of here, so which is this. And this has current candidate. Let me use another color. So currently, this has candidate here, and this has candidate here. So this should go to one of these later. This should go to one of these later. But for now, we are not embedding. We are only embedding this. When we embed this to here, this shrinked into this. So if this vertex has neighbors here, which are all this blue thing, and this less of them is not neighbor, then this yellow set, candidate for this, will shrink to here. So we want to choose vertex which has large neighborhood here. And again, this two here, we want to choose the vertex which is in large neighborhood here. So, what that means is, since p sub psi I and p sub psi SL, so this is p sub psi I, so this is xi is here, so this is x psi I, and this is v psi I, so it's here. And this is in the same manner, so this is v psi S1, because this is x psi S1. So this pair is epsilon regular, moreover epsilon d plus regular. Actually, I forgot to. Oh no, sorry. Yeah, it's okay. So we use this lemma 4.2. Lemma 4.2 implies that the number of vertices in here, entire vertices here, the number of vertices which has small neighborhood in this yellow set, is at most epsilon times the size of this is n, epsilon times n. So those vertices are bad vertices. If you choose that, then this shrinks too much. So those vertices are bad vertex. And for this, also there are epsilon n vertices. So this is also epsilon regular. So there is also epsilon n vertices which are bad for this. And how many these pairs are we have? P pairs, P. P, we have to consider this P time, and P is at most delta. So there is at most delta epsilon n bad vertices here. The rest of them is still good. So lemma 4.2 implies that all but epsilon n vertices in this entire set, in other words, still that many vertices inside of this C sub I, because C sub I is a subset of this entire set, have at least d minus epsilon times C sub I SL. So current candidate set has this size, and then it shrinked into a smaller set by factor of d minus epsilon. Neighbors in C sub I of SL. Yep.
What is n? Maybe you want to say instead of...
N is size of the entire thing. Entire this set. Then hence at least, so size of C sub I minus delta epsilon n vertices in here. This is actually P times epsilon n, but P is at most delta, so delta epsilon n vertices in C sub I has at least d minus epsilon times C sub I SL neighbors in C sub I J. And then, by our assumption, what did we assume? We assume our induction hypothesis that this is still delta plus 1 times epsilon n. That means this is bigger than epsilon n. So still we have epsilon n good choices. Still still we have this epsilon and good choices. And among them, some of them might be already taken to other vertex. Some of them might be already an image of other vertex. But how many? So each xi, so we know that xi are mapped to vi. So x psi I, more precisely, are mapped to b psi I. And this has at most epsilon n vertices. And we haven't still embedded xi yet, so small xy yet. So at most epsilon n minus 1 vertices are already embedded. So one of that must be still not taken. So among them, at most epsilon n minus 1 vertices are already in p sub 1 to p sub I minus 1. Since c sub I minus delta epsilon n minus epsilon n minus 1 is 1, so we can choose one such vertex p sub I which is not an image of previous vertices, which has at least t minus epsilon times c sub I SL neighbors in C sub I SL for L between 1 and P. So after choosing this P sub I, we have to update it. So we have to update the candidate set. So C sub I plus 1 J is either C sub I J intersection with the neighborhood of this Pi if this Xj is a neighbor of this Xi. So this is exactly what we did in here, right? And then if not, we just delete Vi because it's already taken. If this is not the case. So for example, if we have another vertex here which has a xj prime, then after embedding this, its candidate set might shrink by one vertex because we don't want to embed it again to the same vertex. So this is second. But if some vertex here which is non-neighbor, then this doesn't affect anything. So it's same. So this is exactly the candidate set. And then we show that we can actually do this until we finish it. So for each xj, it has at most delta neighbors. So initially its candidate set has, so at any point Ci, it's, so I plus 1 say, okay, any point, its candidate set, it starts from its initial candidate set which has size n, and it might have shrinked by factor of d minus epsilon, how many time? N mod delta time. It has some pre-neighbor, which is N mod delta. And then also, it could lose one vertex if other vertex in same partition is embedded. So let's say we have xj here, and then another vertex, say xj minus 10. If we embed this into some vertex, then this also, affects this candidate set by 1. But how many times that happen? At most size of x psi j time, which is epsilon n. Then, because we know that this equation, this inequality holds, we can easily show that this is still bigger than delta plus 1 epsilon n. So which give us our induction hypothesis. So after embedding xi, this induction hypothesis still holds, so we can keep repeating. So this proves the lemma. So this is clear, right? So what we said. So this embedding lemma asserts that when we have a G which admits this epsilon regular structure, and H which has bounded degree, and then H has compatible structure with this G, then we can embed. Actually, so it's a simplified version of a more complicated statement. So if you see exercise 4.7, so here we said that every BI has size n, but which is not really necessary. It could have, as long as we have some lower bound, it could have much larger size. But later for later usage, it is okay to just have a lower bound and upper bound. So I wrote it that way in exercise 4.7. But only lower bound is, even if it's just that everything is at least n, this is still good. And then, as Sang-il mentioned before, here we have this complete structure. So every pair is epsilon regular, epsilon regular, epsilon regular in G. But that is not necessary if H has compatible structure. So if in H, x1 and x2, there is no H between, then in G, we don't have to have any structure between V1 and V2. And also there are more. So yeah, I recommend you to read the exercise 4.7. So actually there are more things that we can ensure. So yeah, I recommend you to read. So this shows that this epsilon regular structure is very useful for graph embedding problem. And again, still we want to show that this is useful because lots of graph admit this epsilon regular structure. So that's another fact that will be useful for us. So indeed, there is lemma called regularity lemma, which ensures that. So what it essentially says is that for any graph we have, we can partitionate the vertices so that it gives us epsilon regular structure. But of course that is true because let's say we have this simple graph. Then what would be the epsilon regular structure of that graph? What would be the most easy way of finding an epsilon regular structure? So one easy way is we take one vertex, and one vertex. Between this pair, so we have only one vertex and one vertex. Then whatever A prime satisfying that is just the entire thing. B prime satisfying that is the entire thing. So its density is 1. So yeah, I have deleted the definition, but it trivially satisfies the definition. So it is actually true that we can partition any graph into, one vertex, one vertex, one vertex, one vertex, then we get the epsilon regularity structure. But that's not useful because we need I mean, in here, we are using that the n is large, right? So each part should have large size. I mean, we implicitly used n is large because of that and some other, anyway. So, n is large means that so this structure is not really useful. What we want is that we want to make it large. In other words, we want to make the number of parts is significantly smaller than the number of vertices in G. And actually that is possible. So that's what this regularity, summarized regularity lemma says. So theorem 4.4 is the regularity lemma. So for any epsilon, so epsilon is the error parameter we want. So we choose epsilon. We want to find the epsilon regular structure for whatever epsilon we want. And T. And also another, I didn't mention it, for another trivial regularity partition of this is we can take everything by one pilot. But that's also not useful, right? It's trivially, epsilon regularity because we cannot take any. So here we say that this pair is epsilon regular, but there is no pair. So vacuously epsilon regular, but this is not useful. So we want to make sure that the number of parts is not too small and not too large. So this is the lower bound of number of parts that we ensure. So we want to find the epsilon regular partition which has at least this small t number of parts. Then there exists integers large n and t such that the following holds for all n at least this large n. So for all large graph, so n is again the number of vertices in G. And it's at least this large n means we have lots of vertices. Then every n vertex graph G admits a partition p sub 0, p sub 1, p sub r satisfying the following. So first, the number of parts is not too small and not too large. So this capital T is upper bounded and it's fixed. So no matter how large we make this small n, that T is fixed. So that's just constant. So we can make this n much larger than t, t squared or t to the t to the t to the t to the t. So whatever, however n is large, let's say this is R1. T is bounded. And R2 is that p sub 1 I and p sub j has same size for all I, j between 1 and R. Here, it's between 1 and R because this B0 is not mentioned, right? So B0 has special law. So these form an epsilon regular structure, so, but B0 is not. B0 is exceptional set. And that exceptional set has small size. And lastly, rest of the vertex set, V1 to VR, forms an almost epsilon regular structure. So for each I, the pair Vi and Vj are epsilon regular in G for all J except and most epsilon R indices J. Yep. So what it means is that the picture is like this. So if we have G, we can take V0 and V1, V2, V3, V4, V5. And for V1, this is epsilon regular, and this is epsilon regular, this is epsilon regular. But there could be like some exceptional pair which is not epsilon regular. But such not epsilon regular pair are small. In the sense that for V1, most of them are regular. I mean, most of them are epsilon regular except epsilon R of them. So this is just very small fraction. And remember that this small exceptional set, so this doesn't belong to this structure. This is exceptional set. It's small in terms of the entire vertex set. So this is only epsilon n. But what's the size of these things? These things have all same size. That means that's n minus size of V over R. So this is something like 1 minus epsilon n over R. And R is between these two, and these are given by, these are functions of epsilon and t. So this could be much bigger than 1 over epsilon. So that means n over R could be much smaller than epsilon n. So this is small set in terms of the entire graph, but this could be much bigger than this. But altogether, this is much bigger than here, but one by one, this is still big. So
you want J to be not equal to I.
Yes, okay, but yeah, we can say that the I is also in here, but yeah, J not equal to I. Okay. So yeah, we spent a bit more time than I expected, but yeah, there is nothing afterwards, so yeah, I might go over, a bit over, but yeah, I apologize for that, but I will try to speed up. So if you don't right away understand what it says, then yeah, it takes some time. Yeah, I first saw this statement when I was in PhD students, and I was thinking that what the hell is that, and I don't like that. And yeah, for several years, I didn't even understand what it means until I had to use it. Yeah, I was forced to use this theorem in my postdoc year, but anyway. So yeah, it's okay to just to take your time and yeah, you read it several more times, and then later if you use it to apply to another problem. That's what we will do today and tomorrow. Then you will get more used to it. So in order to use it and use this regularity lemma into another problem setting, we define called, okay, it's definition, so let's write it here. We define some tool which help us to analyze this epsilon regular structure. Let's say, so this partition which satisfies this property, we say that that is epsilon regular partition. So first one is regarding the size of partition, so it doesn't have to satisfy that. But if something satisfies R2, R3, R4, then we say that partition is epsilon regular partition. So that's just the language. So for any question? So for a given epsilon regular partition, which is a partition satisfied is R2, R3, R4 of G, which is B0, B1, BR. We say that the R, B, we say graph R is its epsilon delta reduced graph of this epsilon regular partition. If R is defined as follows. So R is a graph consists of the vertices, which is number between 1 and R. So 1, 2, 3, 4, R, those numbers are vertices of R, this capital R. And Ij is an edge of R if and only if P sub I, P sub j is epsilon, say delta plus regular.
레귤러리티로 저 그래프의 토포로지컬 마이너를 위아래로 리듀스드 그래프라고 하는 건가요?
토포로지컬 마이너라고도 볼 수 있죠. Okay, yes, it's kind of like minor, but I mean, so if this is connected graph, you can contract it into one vertex and say it's minor. Yes, I mean, in some sense, yeah, it could be think in similar way, but not exactly same. Yeah. So this contains the information about which pairs are epsilon regular and which pairs have a density at least something. So this is useful because in this embedding lemma, we have this structure that between this pair, we have epsilon regular with certain density, at least something. So these pairs are useful. And if some pairs are not epsilon regular, then it is not useful. And some pairs have too low density, that is also not useful. So this encodes the information about which pairs are useful. So, and that's, so there are again two reasons why it is important, it is useful. Because it encodes the information about this epsilon regular partition. So we can actually use this embedding lemma, I mean, according to this reduced graph R. And another reason, what was another reason? I was thinking two reasons before, okay. Another reason is that it also inherits some property of G. So this is not just an arbitrary random graph, and not by random. This is not just arbitrary graph. When we have G, and we take this epsilon regular partition of G, and then we take this reduced graph, then we can say something about this R based on the property of G. So for example, if you see exercise 4.2, if G has lots of edges, so G has high density, then this R should be also very dense. It makes sense, right? So if we have a G which has a large number of edges, then its partition, we also have large number of edges. Large number of edges means that most of them has high density. And the regularity lemma ensures that most of them are epsilon regular. So R should be also have lots of edges. And similarly, we can also show that if G has large minimum degree, then R also has large minimum degree. Later we will use that fact. So for now, exercise 4.2 only says that if G has many number of edges, then G is quite dense, then R is also dense. So by using that, we can prove the Erython-Simonovich theorem that we have proved before. So that says that so proof of theorem 2.1, so which was Erython and Simonovich theorem. What it says is that if chromatic number of H is say K, at that time we used the letter R, but here we will use R to denote the number of parts, so I will change it to K. And number of edges of G is at least 1 minus 1 over K minus 1 plus delta times N, then H embeds into G, assuming N is large. So that was what Erichsen-Simonovich theorem says that. So in the first day, we proved this by using induction on this K so that we can find the complete multiple type graph, and then H embeds into that complete multiple type graph. But if you use regularity lemma, we can prove it in short way. So suppose that we take N0 much smaller than epsilon and much smaller than delta. So this notation is for fixed delta, there exists epsilon, and for fixed epsilon and delta, there exists N0. So I just shorten it. So we choose that, and then let's say N is bigger than N0. Then what we can do is, sorry, of course it doesn't make sense. Yes, so N square over 2. Yeah, why did I write that? So what we do is apply regularity lemma to G, and we obtain an epsilon regular partition P sub 0, P sub 1, P sub R of G, which satisfies R1 to R4. Those four properties. And let R be epsilon, say delta over 3 reduced graph. Graph of this epsilon regular partition. Then what we know is by this exercise 4.2, because G has lots of edges, this R also has lots of edges. And how many edges? This R should have at least 1 minus 1 over K minus 1 plus, say, delta over 3 R squared over 2. So see, here N is replaced by R, and this number is decreased by small. But still we have this. So I will leave exercise as your, exercise. And what do we know? So it has that much edges. Then in first day, in first lecture, we proved Turan theorem, which says that if it has at least this number of edges, then complete graph on K vertices embed into this R. And without loss of generality, let's say the vertex 1, 2 to R, K forms this complete graph on K vertices. So what does it mean? It means that we have B1, B2, and BK. And all of them are epsilon delta over 3 plus regular, which is exactly what we want in this embedding lemma. So embedding lemma we have, so here is K sets, and all pairwise it's epsilon delta over 3 plus regular. So that provides exactly structure of G in here. And now, can you find the structure for H? For H, we know that it has because its chromatic number is K. Then chromatic number is K. It automatically have a partition x1, x2, xk, which has, each of them is independent. And we need to check that each size of xi is much smaller than vi, which is okay because we take n0 very large. So n is large, and each of this thing has size at least 1 minus epsilon times n over r. And by R1, property R1, this R is at most t, which is constant. So if n is large enough, this is n times some small constant. And n is large enough so that this is much bigger than size of h. Here, h has bounded size. So, by embedding lemma, h embeds into this, this G, in this graph of G between V1 to Vk, which is subgraph of G. So h embeds into G. So this provides this short proof of Ehrlich-Stone-Simonovich. And since this was too easy, let me present you one more application. I will probably be able to finish it in 10 minutes, so I might go over slightly. But so as I mentioned yesterday we proved that when we have a h, which, so in first day we showed that the Ramsey number of k sub r is exponential in size of h. And then yesterday we showed that the Ramsey number of h is bounded by some constant times size of this h if its maximum degree is bounded and h is bipartite. So that's the last theorem that we have proved yesterday by using dependent random choice. And I promised you that we will prove the same thing for non-bipartite graph, for any graph with a bounded maximum degree. So this is we will do. So let me write it. So theorem 4.5 says that if we have this delta fixed, which is constant, and h is a graph with bounded maximum degree, then there exists a constant c which only depends on delta, such that Ramsey number of h is at most c times the size of h. So again, recall that the Ramsey number is the smallest n, such that we have a kn, and we color all the edges by red or blue. Then we have to have a monochromatic copy of h. And we take such smallest n, then that's the Ramsey number. So for this, what we have to show that is that if we take n, which is some constant times of size of h, and we edge color the complete graph on n vertices by red or blue, then we show that either h embeds into red graph or h embeds into blue graph. That's what we have to show. So first, for that, we come up with the constant first. What would be the c? So let's say k is a Ramsey number of k sub delta plus 1. So delta is fixed number, and its Ramsey number is just function of delta. So this is some function of delta. So this is not, h is much bigger graph, and this is some small graph that we take. Later we will use this. So this is actually, so our strategy is as before. So here, how did we do? we take regularity lemma, and then we use Turan theorem to find this copy in R. And then we apply embedding lemma. So here, what we have to find? We have to find this copy in later R, so that all the pairs are epsilon regular in red graph or in blue graph. So we have to find, so what we will do is we will apply regularity lemma to red graph, and then in that reduced graph, we find this copy, all in red or all in blue, so in either case. And then we apply embedding lemma. So for that, to find the monochromatic disk copy, then if we find the disk copy without knowing any colors, then we can always find the monochromatic disk copy inside of here. So that's the definition of Ramsey number. So for that purpose, we let this k be some number. So, and every coloring of k sub k, we can find the monochromatic k sub delta plus 1. And take epsilon, which is 1 over, say, 2 to the delta plus 1 k. And t be k plus 1. Then by regularity lemma, there exists some capital T, which is function of this epsilon and t, which is further a function of this delta. Because epsilon is, so k is determined by delta, and epsilon is thus determined by delta, and t is determined by delta. So everything is determined by delta. So this number is also determined by delta. This number is the one in R1. So later we will use regularity lemma. For that purpose, we take the constant first, and then later we will use regularity lemma later. So this is that number. And n is again the number depending on only delta. So later we will use regularity lemma so that we take this constant. And let C, which is C of delta, with the 3 epsilon negative, epsilon to the negative 1 times Tn. So it only depends on delta. So that's our C that we will use. So now what we have to do is we take n, which is C times size of V, and then show that any two coloring of k sub n, we can find either red copy of H or blue copy of H. So we color, we 2H color k sub n, and let G be a red graph. And apply regularity lemma to G. Then we obtain an epsilon regular partition V sub 0, V sub 1 to V sub R, such that R is at least T, which is K plus 1, and at most large T. So, because of this condition, this is R. For each I, the size of Vi is at least 1 minus epsilon times n over R, and R is at most T, so this is lower bound. And what do we know? We know that the n is at least 3 epsilon to the negative 1 times T times n times size of pH. So even if we delete T, this still has to be, and multiply 1 over epsilon. This is at least twice times epsilon to the negative 1 times size of B, size of H. So this n is here because we can invoke the regularity lemma. So n should be large. And this t is here because we can divide it. So this Vi is still large. So that later we can apply the embedding lemma. For that, the Vi should be large. And we are almost there. So hang on with me. And now we have this partition. And we consider reduced graph, say epsilon 0 reduced graph. So here we don't care about density. And what do we get? We get this reduced graph, which is almost complete. So originally, so because of this zero condition, every pair is in, every ij is in R, unless it is epsilon, it is not epsilon regular. As long as that's epsilon regular, there is a pair in R. So that means R is almost complete. So this R4, the condition R4 says that for all I, the density, the degree of R, degree of I in R is at least 1 minus epsilon times R. So here we put 0, which means that we have I and J. As long as they are epsilon regular, we put H in R. So for R4 says that for each I, for fixed I and all J, they are epsilon regular for all J except at most epsilon R. So we get this.
Can I ask you something?
Yep.
What is capital N?
Capital N is this capital N so that we can apply regularity lemma. It makes sure that the N is large enough we can apply regularity lemma. So, and what do we know? Epsilon is smaller than 1 over K. So this R contains at least 1 minus 1 over K R. Epsilon is smaller than 1 over K. So by Turan theorem, there is copy of K sub K in R.
There should be R squared, right? The number of entries of R.
Correct. Over 2. Sorry. Yeah, I always make this kind of silly mistake. Anyway, so this is the one that we want to find. So we get, say, assume. No, we don't need to assume. So this is what we get. And we have B1 and B2 and B3, BK. And in R, we have these edges. And we now color the graph R. So this is K sub K. So that we color this H red. So color H in R red if its density of G between B sub I, B sub J is at least half. So Hij. Otherwise blue. So that gives us a coloring of R. So coloring of this copy of K sub K. So now we are really almost done. So by the definition of K, K was chosen as the Ramsey number of K sub delta plus 1. What does it mean? So this coloring gives us the 2H coloring of this copy of K sub K, complete group on K vertices in R. So this is complete graph on K vertices, which is 2 colors. So there should be monochromatic copy of. So there exists monochromatic copy of K sub delta plus 1 inside of this R. To be more precise, it's in this KK, and KK is in R, so in here. And if this is lead, then let G prime be G. If this is blue, let G prime be complement of G. So if it's lead, in this case, we know that the Bi and Bj are epsilon regular with density at least half. That was the definition of coloring by lead. So in that case, we apply the embedding lemma, then we are done. But if that's blue, what does it mean? So between this pair, the G has only density less than half. Then in this complement, it has density at least half. So in blue graph, it is at least half. So G complement is blue graph. So the G was taken as a lead graph inside of this Kn. In blue graph, they have density at least half. And it is easy exercise that if you have a graph which is epsilon regular between two sets, and if you take a complement, that is also epsilon regular. Because density 1 and 1 minus t are just flip, and every condition is same. So in here, again, we have in this G complement, we have this partition so that every pair is epsilon regular with the density 1 over 2. And moreover, we ensure that each B sub I is bigger than 2 epsilon inverse size of B of H. And H has a bounded maximum degree. So by Brooks theorem, it admits a partition X1 to X delta plus 1 into independent set. And each independent set is sufficiently smaller than B sub I because we multiply epsilon. So each B sub I is, say, smaller than epsilon times B sub I over 2. So which the all condition in embedding lemma satisfy. So we can embed H into that G prime. So that proves the theorem. So we show that the Ramsey number of H is linear in size of H if H has bounded maximum degree. And there are several more, but one drawback of this is that this constant is quite large because of the regularity lemma. So this constant was, n times t times 3 epsilon inverse. So that was constant. But because of this regularity lemma, it is and t and n are very large number in function of delta. So there is this drawback. So, there are several other methods to prove a better bound. And recently, Jung-Bom Lee generalized this into more general class of graph H, which is not only bounded degree, but just satisfying some degeneracy condition. So that concludes the lecture today, and I hope you will take a look at the exercises to get more familiar with this epsilon regularity concept, because tomorrow we will extensively use it. So I recommend you to prove all the exercise with the stars at least. Yeah, thank you very much.